A doctor cannot say the AI told me to. Explainable AI, XAI, is the set of methods and techniques that make AI decisions interpretable to humans. It answers the question, why did this model produce this output, for this input, at this time? In this video, we explore the methods that make AI decisions transparent, the key concepts in the field, and the high-stakes applications where explainability is not optional. Let us examine the technical landscape of AI explainability methods and why the ability to explain AI decisions is becoming both an ethical necessity and a legal requirement. 5 key methods and concepts define the landscape of AI explainability, from the design of inherently interpretable models to post hoc techniques that explain the decisions of black box systems. The fundamental distinction in AI explainability is between intrinsically interpretable models, whose decision logic is transparent by design, and post hoc explanation methods, techniques applied to explain the decisions of models that are not inherently transparent. Intrinsically interpretable models include linear regression, logistic regression, decision trees, and rule-based systems, all of which allow a human to directly inspect the model's parameters or decision rules to understand why a particular prediction was made. Post hoc explanation methods, including SHAP, LIME, and attention analysis, are applied to black box models such as deep neural networks and gradient-boosted trees after the fact, approximating or attributing the decision to understand it without full access to the model's internal mechanics. The choice between interpretable models and black box models with post hoc explanations is a fundamental design decision in any AI system where explainability is a requirement. SHAP, Shapley additive explanations, is the most theoretically grounded and widely adopted method for explaining individual predictions of black box machine learning models. SHAP assigns each input feature a value, its Shapley value, that represents its marginal contribution to the model's prediction for a specific instance, calculated by averaging the feature's contribution across all possible subsets of features. The result is a consistent, locally accurate attribution that answers the question, how much did each input feature push this prediction above or below the baseline? SHAP values are additive. They sum to the difference between the model's prediction and the mean prediction, which makes them interpretable as a decomposition of the prediction into the contributions of each input. Positive SHAP values indicate features that push the prediction upward. Negative values indicate features that pushed it downward. LIME, Local Interpretable Model Agnostic Explanations, is a practical post hoc explanation method that works by approximating a complex model's behavior in the neighborhood of a specific prediction with a simpler, interpretable model. To explain a particular prediction, LIME generates a set of perturbed versions of the input, slightly modified copies, runs them through the black box model to obtain predictions, and fits a simple linear model to this local dataset. The linear model's coefficients indicate which features are most important for this specific prediction in this local region of the input space. LIME's key practical advantage is that it is model agnostic. It works with any model that can produce predictions for arbitrary inputs, regardless of architecture, making it applicable to the full range of black box models in production use. Attention weights in transformer models offer a natural candidate for post hoc explanation because the attention mechanism explicitly computes scores representing how much each token in the input influences each token in the output. Visualizing attention weights can reveal which input words or phrases the model focused on when generating a specific output, providing an intuitive form of explanation for text-based AI systems. However, the relationship between attention and explanation is contested. Research has shown that attention weights do not always correspond to causal importance. High attention tokens are not necessarily the most causally influential features in the prediction. Practitioners should treat attention visualizations as useful diagnostic tools for understanding model behavior rather than as rigorous attributions of causality. The right to explanation is a legal concept that is reshaping the mandatory explainability requirements for AI systems in regulated contexts. GDPR Article 22 grants individuals the right not to be subject to solely automated decisions with significant effects, and Recital 71 indicates that individuals should have the right to obtain a meaningful explanation of the decision reached. The EU AI Act goes further, requiring that high-risk AI systems be transparent enough to enable deployers to explain individual decisions to affected persons upon request. These legal requirements are driving the adoption of explainability methods in lending, insurance, employment screening, and other high-stakes automated decision-making contexts, transforming explainability from a research interest into a compliance obligation. For essential terms that define the technical vocabulary of explainable AI and the methods used in practice. SHAP is grounded in cooperative game theory, specifically in the concept of the Shapley value, which provides a fair attribution of a jointly produced outcome to each contributing player. In the machine learning context, the players are the input features, and the jointly produced outcome is the model's prediction. The Shapley value for each feature is computed as the weighted average of the feature's marginal contribution across all possible orderings of features, a calculation that ensures the attribution is consistent, locally accurate, and globally meaningful. SHAP has become the dominant explainability method in production AI systems because it produces attributions that are mathematically well-founded, visually interpretable through waterfall and summary plots, and applicable to any model that can produce predictions, regardless of architecture. LIME addresses a fundamental practical challenge in AI explainability: how to explain the prediction of a complex model without access to its internal structure or gradients. LIME's solution is to treat the model as a black box and study its local behavior empirically by querying it with perturbed versions of the input. For a tabular data prediction, LIME randomly masks subsets of features and records the model's predictions for each masked version. It then weights these perturbed samples by their proximity to the original input and fits a sparse linear model to predict the black box model's outputs. The linear model's coefficients are the explanation. They identify which features have the largest local influence on the prediction. LIME is particularly useful in contexts where computational budget does not allow for the exhaustive feature subset sampling required by SHAP. Interpretability is a property of model architecture rather than of explanation method. It describes the degree to which the model's own structure, parameters, and decision logic are comprehensible to a human analyst without the need for additional explanation tools. A logistic regression model is highly interpretable. Its coefficients directly express the log-odds contribution of each feature, and any analyst can read the model parameters to understand its decision logic. A deep neural network with millions of parameters is not interpretable in this sense. No human can read its weights and understand its decisions. The distinction matters because interpretable models offer verifiable transparency. Humans can audit the model logic directly, while post-hoc explanations of black box models are approximations that may not faithfully represent the model's true decision process. Post-hoc explanations are the practical solution for applying explainability to the high-performing black box models that dominate production AI. Rather than constraining model choice to interpretable architectures, which often sacrifice predictive accuracy, post-hoc methods allow organizations to use the best-performing model for each task and then apply explanation techniques to understand individual predictions after the fact. The critical caveat of post-hoc explanations is that they are approximations. They describe what the model appears to have done for a specific input rather than providing a guaranteed causal account of the model's internal computation. Practitioners must understand this limitation and communicate it clearly to stakeholders who rely on post-hoc explanations to make decisions about model deployment, regulatory compliance, or individual case adjudication. Let us now look at how AI explainability methods are being applied in high-stakes domains where the ability to explain individual decisions is essential for compliance, trust, and accountability. Across finance, healthcare, fraud detection, and regulatory reporting, explainability is enabling organizations to deploy high-performing AI models while maintaining the transparency required by law and by ethics. Loan decision explanations represent one of the most mature and legally mandated applications of AI explainability. Regulators in the US, EU, and UK require that lenders explain adverse credit decisions to applicants, specifying the principal reasons their application was declined or their loan terms were less favorable than the best available. AI-driven lending models that use SHAP or similar attribution methods can automatically generate adverse action notices that identify the top factors: high debt-to-income ratio, short credit history, recent missed payments, that drove a specific decision for a specific applicant. This explainability capability is what allows AI to replace or augment human underwriters in lending decisions without violating the consumer protection regulations that require human comprehensible explanations. Medical AI applications are among the most demanding contexts for explainability because the consequences of errors are severe. Clinicians are trained to understand and communicate clinical reasoning, and regulatory approval of medical AI devices increasingly requires evidence that the system's decisions can be explained and validated by clinical experts. Explainability in medical AI allows a radiologist to see which regions of a scan drove a diagnostic prediction, highlighting the specific tissue features that the model associated with a malignancy, and to evaluate whether those features align with their clinical judgment. This integration of AI-generated explanations into the clinical workflow supports rather than supplants physician decision-making and is essential for building the trust that drives clinical adoption. Fraud detection is a domain where explainability serves multiple simultaneous functions. It helps fraud analysts understand and investigate flagged transactions, enables model debugging when the fraud detection model starts flagging legitimate transactions incorrectly, and provides the audit trail that compliance teams need to demonstrate that fraud decisions are made on legitimate grounds rather than on protected characteristics. Feature importance explanations for fraud alerts, identifying that a transaction was flagged because of an unusual geography, atypical amount, device fingerprint mismatch, and velocity anomaly. Give fraud analysts the context to make faster and more accurate adjudication decisions and reduce the false positive rate by enabling analysts to override flags that the explanation reveals are based on coincidental rather than causal risk factors. Regulatory reporting with explainable model outputs is a growing compliance requirement across financial services, insurance, and healthcare as regulators increasingly require that regulated entities demonstrate they understand the basis for consequential automated decisions. Stress testing and model risk management frameworks require financial institutions to document their model's decision logic and sensitivity to key input variables. Insurance regulators require that rate-setting models be explainable and free from discrimination on protected characteristics. Healthcare regulators require that AI medical devices be clinically validated in ways that require understanding the model's decision basis. In each case, post-hoc explainability methods provide the attribution reports and sensitivity analyses that regulators use to evaluate whether the model's behavior is appropriate, lawful, and safe. Let us bring together the essential points from our exploration of AI explainability. To explore more key concepts in generative AI, check the link in the description. If you found this helpful, please like and subscribe. Thank you for watching. If you found this helpful, please like and subscribe. See you in the next video.